Okay, so we're doing some problems with Watt's law here. So there were a couple of different forms of Watt's law that we use. Can anybody remind me of one of those forms?
Okay.
Yeah.
Power is I times V.
Yeah. Power equals current times voltage. We could also write this another way, right? We could write it sort of the way that we did Ohm's law, right? So we can use that in either way. There were a couple of other forms also. Anybody remember? Yeah.
Power is equal to current squared times resistance.
Sure. Good. And one more? Yeah.
Power equals voltage squared divided by resistance.
Yeah. Exactly. So these were all different ways of writing Watt's law. They're different ways of finding the formula depending on what information you have. So if you have the current and the voltage, you can use this form. If you have the current and the resistance, you can use this form. And if you have the voltage and the resistance, you can use this form. So this first problem, we're given the voltage and the current. So which of the three forms should we use? Yeah, probably the first one, right? Because that one has power, current, and voltage. So we can say power equals current times voltage, or in this case, it's 0.1 amps times 10 volts. Remember, we want to convert 100 milliamps into raw units before we do any calculations. So we convert 100 milliamps into 0.1 amps, and then we do the calculation. So 0.1 times 10 equals exactly 1 watt. So this first resistor is dissipating 1 watt of power. Okay. So in the second problem, we're given the power and the resistance, and we're asked to find the current. So which one of these forms can we use? The middle one, right? That has power, current, and resistance. So if you're comfortable with algebra, you can take this and rearrange it. If algebra is a little bit of a sticking point for you, that's fine. We have the formulas rearranged and written out in a nice table in the lab book, so you can take a look at that as well. So in this case, we can say I is the square root of P over R. So that is the square root of 0.25 divided by 200. So what does that come out to be?
50.
What's that?
35 again?
Okay, so 0.035 amps, or 35 milliamps, right? Any questions about that? Okay, so that's how we can calculate power, but let's remember a little bit about what power actually is. Right? Power is the work that electricity is doing. So it's how much your energy is actually doing for you. So we talked about the analogy of water hitting a water wheel and making the wheel turn. The amount that the water was making the wheel turn was the power that was being generated. So we said that if we just had a small amount of current and a large voltage, then the wheel would only turn a little bit. If we had a large current but a small voltage, the wheel would only turn a little bit. We really needed both current and voltage to get a lot of power. So you need both of those in order to generate the power. Any questions about that? Okay. So today we're going to talk about series parallel circuits. In the past we've talked about series circuits and parallel circuits by themselves. Today we're going to look at circuits that have some series and some parallel elements in them. Okay? So we're going to do a brief review of series circuits, a brief review of parallel circuits, and then we're going to look at series parallel circuits that have both elements in them. Okay? For the lab today, we're going to have some multi-sim and some hands-on stuff just like usual. The multi-sim will involve taking series parallel circuits and simplifying them. Okay? A lot of the trick to analyzing series parallel circuits is simplifying them so that they get easier and easier to understand. So we'll see about that. And then you'll get to do some examples of that in multi-sim. And then you're going to make a couple of series parallel circuits yourself. You're going to construct one on a breadboard, and you're going to look at that lamp board that we saw last time. You're going to use that again, but you're going to use a slightly different configuration. You're going to connect it up so that it makes a series parallel circuit instead of just the two parallel lamps like we saw last time. Okay? So, any questions before we get started? All right. So let's briefly review series circuits. What we saw was that series elements are circuit elements that are connected end to end. So the start of one element is connected to the end of the previous element. They're almost like trains on a train track, right? So an example of a series circuit would be something like this. You've got two resistors that are connected end to end. So they're in series. And we said that with series circuits, is the current the same or different through the resistors? The same. Yeah. What about the voltage? Is it the same or different? Yeah. So the voltage can be different across each resistor. Another way of thinking about this is that voltage is the same along any wire, and current is the same along any path. Okay? So the voltage is the same at every point along this wire up here. So if you have, say, 10 volts here, you're going to have 10 volts over there as well. And 10 volts in the middle, and 10 volts at the corners, and 10 volts everywhere along this wire. But when you have a component in the way, then the voltage can change. The voltage can often be different on different sides of a component. So you might have 0 volts down here. So then you'd have 0 volts everywhere along this wire, but a different voltage after the component, right? So the voltage is always the same along any wire. The current is the same along any single path. So there's only one path from the top of this battery or power supply through this whole circuit. There's only one path that the current can travel from the positive side to the negative side. So the current has to be the same along that entire path. Okay? All right, so for series circuits, the current is the same everywhere, and the voltage is different. Now, for parallel circuits, does the current have to be the same everywhere?
No.
No, exactly. With parallel circuits, there are multiple paths that the current can take. So some of it can go down this path, and some of it can go down this other path, and it doesn't have to be equally divided between them. So you could have 500 milliamps coming out of the power supply, for instance, and you could have 200 milliamps traveling down the first path and 300 traveling down the second path. So with parallel circuits, the current can change for various elements. But what about the voltage? Does that change? Right, voltage stays the same. And that's because the voltage is constant along any wire. So if we call this point 0 volts down here, then you have 0 volts there and there and there and everywhere at the bottom of each component, because the same wire is connecting the bottom of the power supply to the bottom of the first resistor and the bottom of the second resistor. So you've got 0 volts at the bottom of every component. Similarly, if we said that we had 5 volts up here, for example, then you've got a single wire connecting the top of your power supply to the top of the first resistor and the top of the second one. So you've got 5 volts at the top of every component as well. So the voltage stays the same in parallel circuits. Okay. So with both series and parallel circuits, we were able to redraw the circuits as simpler versions, right? We could find equivalent resistors and redraw the circuits, right? So how did we find an equivalent resistor for a series circuit? What formula did we use? Yeah, we just added them up. So that was fairly easy. What about with a parallel circuit? Yeah, we use this other, 1 over R total equals 1 over R1 plus 1 over R2. Okay. So when we look at series parallel circuits, we're going to be using the same techniques that we used with series circuits and with parallel circuits. We're just going to be using those techniques several times. Okay, so let me show you what I mean. Imagine that we had a circuit that's like this. This is, say, 20 volts here, and then we've got one resistor up here. Maybe this is 100 ohms. So we've got one resistor up here, which is 100 ohms. Then we have two resistors on the right-hand side, which are 400 ohms each. And then we have one resistor on the bottom, which has a value of 700 ohms. Okay, and I might ask you to find the total voltage, the total current, the total resistance, and then the current and voltage for each resistor. And what we're going to do is we're just going to apply the same techniques that we used before. We're just going to do them more times, okay? So what we did before is that we looked at the circuit and we simplified it, right? If we found it was a series circuit, we simplified it, or if it was a parallel circuit, we simplified it. So when you look at this circuit, do you see any elements that are in series or in parallel as it stands?
Mm-hmm.
Yeah? What do you see?
The 400 ohms resistors are in parallel.
Yeah, exactly. These two resistors on the right-hand side are in parallel. We know because the start of the first resistor is connected to the start of the second resistor, and the end of the first resistor is connected to the end of the second resistor. Right? They're sitting side by side. So since these resistors are in parallel, we can find an equivalent resistor using the parallel formula. And then we can redraw this circuit in a simpler way. So what we can do is we can redraw this circuit, and we'll leave the top and bottom resistors in place. So this is still going to be 100 ohms, and this is going to be 700 ohms. And then we can redraw these two resistors as one simpler resistor. So what would be the equivalent resistor for two 400 in parallel? Yeah, 200 ohms. Right? Remember, when we have two of the same resistance in parallel, we can use that simpler formula, right? The equivalent resistance is just half of either one of the existing resistors. So this has an equivalent resistance of 200 ohms. Okay? So we've simplified this circuit a bit, but we'd like to get it down to just one resistor. So do you see any resistors in series or parallel in this second circuit? Yeah?
Well, the circuit is in series, now resistors are all in series.
Yeah, exactly. All of the resistors are in series now. Right? The end of the first resistor connects to the start of the second one, the end of the second one connects to the start of the third, and then the third one connects back to the power supply. So they're all in series. So we can simplify this and draw it as just one single equivalent resistor. So how much resistance would this equivalent resistor have? Yeah, 1,000 ohms. For series resistors, you just add up the existing resistors. So this adds up to 1,000 ohms. Okay? So we took this complicated series parallel circuit and we just looked at it step by step, right? We looked to see if there were any elements in series or parallel, and then we simplified whatever we could, and we just kept going until we got down to a single resistor. Okay? So now we can answer how much voltage we have, right? The voltage is just the voltage from the power supply, so that's 20 volts. What about the resistance? We can put that down now too, because we figured that out. So that's 1 kiloohm. We haven't figured out the total current yet, though. How can we figure out the total current?
Just divide the voltage by resistance.
Yeah, we can use Ohm's law, right? So Ohm's law is written like this. So we're trying to find the current. We say I equals, and then we cover up I, and we see it's V over R. So that's 20 volts, and then we use our equivalent resistance. So that's 1,000 ohms. So our total current comes out to be 0.02 amps or 20 milliamps. Okay? So we can write that over here. Any questions about how we got that? Okay, so what we can do is we can draw that in. We can say, I know that I have 20 milliamps flowing here. That's our total current. So that must be the total current for this circuit. And for this circuit too. Okay. So that's cool. Can we fill in any other values by knowing that total current? Yeah, exactly. So we know that we'll call this one R1, R2, R3, and R4. We know that the current is the same along any single path, right? So we have 20 milliamps flowing this way, and it doesn't split off before it goes through this resistor. So all of that current has to go through this resistor, right? So how much current do we have through this resistor? Exactly, 20 milliamps. Also, we know that the return current is the same as the current going out of a power supply. So how much current do we have coming back here? 20 milliamps, exactly. And since there's no split in the path between this resistor and the return, we know that we must have 20 milliamps there also. So we can say that the current for R1 is 20 milliamps, and the current for R4 is also 20 milliamps. Okay? So if we know the currents for those resistors, we can figure out the voltages for those resistors as well, right? Because we can use Ohm's law. So again, Ohm's law is V, I, and R. So in this case, we're trying to find the voltages. So we say VR1 equals, we cover that up. We see that it's I times R, right? So it's IR1 times R1. So what is IR1? Now I is the current, right? Yeah. So that's 0.02 amps times, and R1 is 100 ohms. Yeah? So 0.02 times 100 equals how many volts? 2 volts. So we can say that there is a 2-volt drop across that resistor. The right-hand side is 2 volts lower than the left-hand side. Okay? And we can do the same sort of calculation for this resistor down here, R4. We can say VR4 is IR4 times R4. So IR4 is still 0.02 amps, and R4 is 700 ohms. So when you multiply that out, how much voltage is that? 14 volts. So there is a 14-volt drop across this resistor. The left-hand side is 14 volts lower than the right-hand side. We can say VR4 equals 14 volts. Okay? Any questions about that so far? Okay. Now we need to find the current and the voltage through these two resistors, R2 and R3. There's a couple of ways that we can do that. First of all, let's look at the current. Okay, we know that we have 20 milliamps flowing here. And then we have 2 paths for that current to go down. Right? If both paths have the same amount of resistance, then both paths get the same amount of current. So they would split the current evenly. So how much current should be flowing down this side?
10 milliamps.
Yeah, 10 milliamps there, and the same on the other side, right? So the current divides half and half because each side has the same amount of resistance. But there are other ways of looking at this also. We know that there's 20 volts of difference between the top and the bottom of this power supply. So what we could say is that the total of all of these voltages has to add up to 20. Okay? So we've got 2 volts there, we've got 14 volts down there, so that adds up to 16. So the remaining 4 volts have to be across these components over there. So you could look at that and you could say that this is 4 volts there. And this is 4 volts there. Equivalently, you could say that this is 20 volts and you're going down by 2 volts. So you must have 18 volts there. Here you have 0 volts along this wire, and you go up by 14, so you must have 14 volts there. So the difference between these two is 4 volts, right? So that's another way of seeing that you have 4 volts there. Yet another thing that you could do is you could look at this equivalent circuit that we have drawn, and you could look at the current flowing through it. So you say that there's 20 milliamps flowing through each of these things. So there must be 20 milliamps flowing through this resistor. This resistor is equivalent to those two. So you can say 20 milliamps times 200 ohms comes out to be 4 volts. That's Ohm's Law. So you could use Ohm's Law with this circuit. say that there's 4 volts across this resistor, and that's equivalent to those, so there must be 4 volts across those resistors as well. So there's several different ways of doing this, all right? You can use whichever way makes the most sense to you. In any case, we said that there is 10 milliamps in that R2 and 10 milliamps for R3. And then the voltage for R2 and R3 is the same, 4 volts and 4 volts. Okay? Questions about that? Yeah.
You subtracted 20 from 2, or 2 from 20, and then you got 18.
Yes.
And then you subtracted the bottom.
So,
How'd you get 4 volts? That's what I'm asking.
right. Yeah. So what's happening is that the current is flowing from. I'm going to draw the current flowing from the positive terminal of the battery to the negative terminal of the battery. That's called conventional flow. That's the way that I learned it. So that's the way that I always draw the current flowing. So the current always flows from a positive voltage to a negative voltage. So for this particular resistor, the current is flowing left to right, so the left-hand side is more positive than the right-hand side. On this bottom resistor, the current is flowing back this way, so it's flowing right to left. So in this case, the right-hand side is more positive than the left-hand side. So we started off with 20 volts at this point, and then we go down by 2 volts, right? So we end up with 18 there. In this case, we know that we have 0 volts here, and that the right-hand side of the resistor must be 14 volts higher than 0. So that means that we must have 14 volts at that point. So we have 18 volts on top of these resistors and 14 volts below them. So the difference across them is 4 volts. Does that make sense?
Okay, and total voltage is 20.
Yeah, the total voltage is 20 volts.
Okay.
Yeah. Questions?
In the resistor, we have the polarity on the left side is positive and negative. How do you know it's you have to subtract?
Well, that means that the left-hand side is more positive than the right-hand side. And I know that the difference across that resistor is 2 volts. So I know that the right-hand side must be 2 volts lower than the left-hand side. So I know that I have to subtract 2 volts from whatever's over here, which is 20 volts. Is that? So the current always flows from the positive terminal to the negative terminal. So I know that it's starting from here and flowing away from here. So I know it's flowing in this direction, from left to right at the top of the circuit. So I know that the right-hand side must be more negative than the left-hand side. Right? And then Ohm's Law tells us how much of a difference there is. We used Ohm's Law and we figured out that there was a 2-volt difference across this resistor. And this polarity tells us that the right-hand side must be 2 volts less than the left-hand side. Does that make sense? Okay, so I know that's kind of complicated. Let's do one more example and try and cement this a little bit clearer, okay? All right, so let's imagine a circuit like this. We've got a power supply here, and then we've got two resistors like this. Say this is 300 ohms, and then this is 700 ohms. And then we've got other resistors over here. Say this one is 200 ohms, and this one is 50 ohms. Okay. And again, we've got 20 volts over here. So I might ask you, what's the total voltage, the total resistance, the total current, and then the current and voltage for each resistor. So we'll call this R1, R2, R3, and R4. So what we're going to do is we're going to just take this one piece at a time. We're going to try and simplify this circuit and simplify it several times. So do you see any elements that are in series or in parallel? Yeah, what do you see? Sure.
Well, each branch, the resistors are in series with each other,
Yeah,
and then the branches are in parallel with each other.
yeah, exactly. So you've got so the first branch, you've got two resistors that are in series, right? So we can redraw those two resistors as just a single resistor. And how much resistance does that one have?
1,000.
Yeah. Right. We know that when we have resistors in series, they just add together. So we've got 300 plus 700, that's 1,000 ohms. And then this other resistor, these two are also in series, right? So we can redraw those as just a single resistor. And in that case, it's 250 ohms. Okay? So can we simplify this circuit any further?
Yes.
Okay, how would we do that? Yeah, so right, we've got two resistors that are in parallel now. So we can simplify those. And we can't just use the easy formula that we used last time, because that only applies when both resistors are the same. And here the resistors are different. So we have to use the more complicated formula, right? So we say 1 over RT equals 1 over R1 plus 1 over R2. So when you plug that into your calculator, what resistance do you get? 200 ohms. Cool. So we can say that this circuit has an equivalent resistance of 200 ohms, right? Any questions about how we did that simplification? All right, cool. So once we know the total voltage, which is just the applied voltage in volts, and we know the total resistance, we can use Ohm's law to figure out the total current, right? So we say I equals V over R. So this is 20 volts over 200 ohms. So what does that come out to be? Yeah. So 0.1 amps or 100 milliamps. Okay? So that's our total current. Cool. So we know that we have 100 milliamps there. Milliamps there. Milliamps there. So what we can do now is we can use this intermediate circuit to figure out the current that's going through each branch. Okay? We know that we have 20 volts across each branch, right? Because this is ground, this is 0 volts all along the bottom of each branch, and we have 20 volts from the power supply along the top. So we can figure out how much current we have flowing through each branch of the circuit. So we can figure out the current that's flowing down there. We can say, we can use the same formula of Ohm's law as we used over there. We say I equals V over R. So in this case, V is 20 volts and R is 1,000 ohms. So then, in that case, we have a current of 20 milliamps. So we have 20 milliamps flowing down this branch of the circuit. That means that we have 20 milliamps flowing down that branch of the circuit also. Okay? So if we have 100 milliamps flowing in here and 20 of it come down this way, how much is left over to go down the other branch? 80, exactly. So we have 80 milliamps flowing over there. So now we can use that information to fill in the current for each of the resistors, right? Because we know if we've got 20 milliamps flowing into this resistor, it doesn't have anywhere to go except into the next one. So all of it has to go into R2. So we must have 20 milliamps going through R1 and R2. Similarly, we have 80 milliamps coming down through R3, and it can't split off or go anywhere else except through R4. So we have 80 milliamps going down there also. So I3 and I4 are both 80 milliamps. Okay? Any questions about how we got that? All right, so then once we know the current for each of these resistors, and we know their resistances, we can figure out the voltage for each of them. So we know that V equals I times R. So 20 milliamps times 300 ohms. So for R1, this is 0.02 times 300. So that's 6 volts. You can do the same thing for R2. You get 0.02 times 700. That comes out to be 14 volts. Here, you can do the same calculation. You get 0.08 times 200, which is 16 volts, and 0.08 times 50, which comes out to be 4 volts. So those are the voltages for each of the resistors. Any questions about that? I didn't do out all of the calculations because it's just the same formula over and over again, but that's how it comes out. So 6 volts, 14 volts, 16 volts, and 4 volts. So we took this complicated circuit that had some elements in series and some elements in parallel, and we simplified it step by step. We looked to see which elements were in series. We simplified those first and redrew the circuit like this. And we saw that we had 2 resistors in parallel, so we could simplify them into one single resistor. Right? And then once we had this single resistor, we figured out the total current. Then we figured out the current through each branch. And then once we knew the current through each branch, we figured out the voltages for each of the components. So the basic procedure that you do is you start off by simplifying your circuit as much as possible, and then finding the current through the simplified circuit, and then working your way backwards to get the answers for the more complex circuit. Yeah?
Could you explain again how you got 200 for the resistance zone?
Sure. So what we did is that we looked at this first circuit, and we said that this left-hand branch had 2 resistors in series. So when we had these 2 resistors in series, we knew that we could simplify that as a single equivalent resistor by adding these 2 together. So that's what we did here. We added 300 and 700 to get 1,000 ohms there. Similarly, this right-hand branch of the circuit had 2 resistors in series, so we simplified that branch by adding 250 ohms together to get 250 total. And then we looked at this circuit and said that we had 2 resistors in parallel. Since these resistors are not the same, we used the more complicated version of the parallel resistance formula. We said 1 over R total is 1 over R1 plus 1 over R2. So we plugged in the numbers here. We said 1 over R1 is 1 over 1,000, and 1 over R2 is 1 over 250. So if you plug that into your calculator, this comes out to be 0.001, and then plus 0.004. So when you add these together, they come out to be 0.005. So 1 over our total equals 0.005. So our total equals 1 over 0.005, which equals 200. Okay? Yeah?
Can you repeat how you split the current between the two?
Sure.
Yeah, so I'm confused. Yeah.
Sure. So what we did is that we looked at this second circuit, and we said that there was 0 volts at this point right there. And that point is connected to the bottom of this resistor and the bottom of this resistor. So there's 0 volts all along this wire. So there's 0 volts at the bottom of both of the resistors. Similarly, there's 20 volts at the top of this power supply, because it's 20 volts greater than the bottom, and the bottom is at 0. So there's 20 volts there. So there's also 20 volts up here at the top of this resistor and 20 volts at the top of that resistor. So there's a 20 volt difference across this resistor. So what we did is we said, well, I know the voltage across this resistor and I know the resistance, so we can figure out the current. We say I equals V over R, so that's 20 volts over 1,000 ohms, so that comes out to be 20 milliamps. So we know that there's 20 milliamps flowing down through that.
And you just did that for the other side too. Is that how you got the 80?
Well, so what I did is that you could do that for the other side.
Oh.
And if you did that calculation, you would see that there's 80. But I did it a slightly different way.
Oh, because you know there's 100, so you just, okay.
Exactly, right. You know that there's 100 coming this way, and 20 of it goes down, so the rest of it has to go the right.
Okay.
Yeah. So in electronics, there's often more than one way to get the right answer. There's also a lot of ways to get the wrong answer, but there are often several ways to get the right answer. So you can pick whichever one makes sense. And oftentimes, it's helpful to try several of them and make sure that you come up with the same thing, right? So it would be a good idea to do the calculation here and make sure that you get 80, and then check that 80 and 20 add up to the current that you have flowing in.
But if there are 3, you'd have to do that on all 3 because there are 3 resistors.
Right,
Yeah.
right. If there were 3 resistors in parallel, yeah, you could do the same calculation on each one of them and figure out how much current is going through each one. Yeah. Other questions? Okay, cool. All right, so that was what I wanted to say about series parallel circuits. Really, you just take what you already know about series circuits and parallel circuits, and you use that to simplify the circuit several times and work your way from there. Okay? So it's not too bad, hopefully. So for homework, I'd like you to take the series parallel challenge from the challenge software. So that's one of those problems from that software that we have in the labs that you can download from Canvas and do on your home computer, or you can do it in the lab, whichever is easier for you. Also for homework, please read about Kirchhoff's laws. Those are in the textbook on pages 109 through 112. Okay? We'll talk about those next time. But now let's go on to the lab. So briefly, this is the Electronics ARC YouTube page. If you go to the videos section, there's me standing up and doing the lectures. So far we have Ohm's Law, Watt's Law, and the Solar Lab. The Solar Lab is labeled L18 because oftentimes we do it later in the year. Like I said, this year we did it early so that we could take advantage of the nice weather. Okay? All right. For today's lab, we're going to start off with a little bit of multisync. So you're going to go to Instructor Files and then ET302, and this is under L11, the Parallel Resistors lab. I'm sorry, L17, Series Parallel. So the first circuit that we have is going to be 2 branches that are in parallel, and each branch has 2 resistors in series. So you are going to calculate the resistance for branch A and then the resistance for branch B, and then you will use the meter here to find the total resistance. So what would we expect the resistance to be for branch A? 2, yeah. You have 2 resistors in series, each one is 1 ohm, so they add together and you get 2 ohms there. Same thing for the right-hand branch. So if you were to draw a simplified circuit, it would be a circuit with 2 resistors in parallel, each one being 2 ohms. So what do we expect the equivalent resistance to be for that circuit there? 1 ohm, exactly. Since they're the same value, we can use the simplified version of the formula. We just divide it by 2 and find that that's 1 ohm. So when we measure this resistance, hopefully we'll see a total resistance of 1 ohm. And that's what we see. So you'll fill in your table, you'll fill in the calculated resistance for branch A, the calculated resistance for branch B, and then the measured total resistance. Okay? You'll do that, you'll change the resistor values around a little bit. So you'll start with 1 ohm each, and then 2 ohms, and try a few others as well. For the second part, you're going to do a similar thing, but now you've got 3 branches. So you'll just put different resistor values in each branch and calculate the resistance for each branch individually, and then find the measured resistance of the entire circuit. Part C is a little bit trickier. So part C, what's going on is that we're looking at this first circuit, circuit 1, and we're trying to do what I did on the board, where we take a complicated series parallel circuit and simplify it step by step. Okay. So we take this complicated circuit that has 3 branches with 2 resistors in each branch, and then we want to simplify it so that we have a circuit with 3 branches but only 1 resistor in each branch, right? And then we want to take this circuit 2 and simplify it even more so that we just have a single resistor. Okay? So what we're doing is we're taking this first circuit, and then we would modify the second circuit to make it look like the first circuit. Okay, so we can look at the current for the first circuit. We're trying to measure the current for these circuits. So we can see that this circuit has a current of 10 amps. So what we would want to do is we would want to modify the second circuit to match the first circuit. So when we measure the current through the second one, it should also have a current of 10 amps. Okay, so how would we do that? What resistance would we have for branch A here? Exactly. Branch A includes 2 resistors in series, so we add those up and we get a value of 8 ohms. What about branch B? How much resistance? 8 ohms. Perfect. And then branch C? 4 ohms. So now when we measure the current through both of these circuits, they should be the same. Yeah, so 10 amps and 10 amps. So then you would do the similar thing for circuit 3 down here. you would modify this one so that it had the equivalent resistance of circuit 2 and circuit 1. All right? So that's what you're doing. You're taking the first circuit for granted, and then you're modifying the second and third circuits so that they are simpler versions of the first one. Okay? Questions about that?
Yeah, it says print out the multi-sim circuit. You
Oh.
also print it out?
No, please don't do that. Thank you, that's a typo. We'll have to get rid of that.
You get a point, right?
Yes, remind me of that.
2 points because the other section has the same.
Ah, okay. All right. Yes. Right, so the next part of the lab is very similar. You start with a slightly different circuit, but you do the same thing, okay? So you guys should be able to get through that. And that's the end of the multisim part. Any questions about multisim? All right. So then, let's go on and look at the hands-on part. So the hands-on part of the lab asks us to start by building a circuit like this. So this is going to be a circuit in a breadboard. We're going to start off with 12 volts of power moving from the left-hand side here. So I like to use the top and bottom long rails of the board for my power. So I'll apply the positive side of my voltage supply there, and the negative supply to the bottom rail here. Okay? So now I've got my power attached, and then this shows a 1 kilo ohm resistor with one side of the resistor attached to 12 volts. So I'll take one resistor and I'll go from here over to the middle of my breadboard somewhere. Doesn't matter exactly where, but just some spot in the middle of the breadboard. Got that? Now there's a resistor going from the end of that resistor across to another one. So I will take my second resistor. I'll put the first leg into the same row as the first resistor. So those two will be connected. And then the second leg is going to go on the other side of this middle channel. Okay, so the second resistor is connected to the first resistor, and the second leg of the second resistor is on the opposite side of the channel. Finally, for R4 here, that's connected from the bottom of R2 back to the power supply, the negative side of the power supply. So I'll put one leg of R4 connected to the second leg of R2, and then the other leg of R4 will go over there. Now I have to add in R3 as well, so I'll use some jumper wires for that. I see that the top of R2 is connected to the top of R3, so I'll put in a jumper wire from the top of R2 over to somewhere in my board. And then I'll put in R3 across that middle channel again. So one side of R3 is going to be in the same row as the jumper wire. The other side of R3 is going to be on the bottom of the channel there. And then I'll take one more jumper wire to make this connection from the bottom of R3 to the bottom of R2. So I'll put this one side of the jumper wire in the bottom of R3, and then the other side of the jumper wire next to the bottom of R2. And that's my circuit. Any questions about that? Yes?
On the sheet, it says total R, so are they putting resistance or total voltage?
I'm sorry, where is that?
On the first one, or measured voltage,
Oh,
is
Voltage.
Oh. I see. So I think that's the voltage across the total resistance. So
Oh.
so you should put in the voltage there.
Oh, okay.
I'm sorry?
Total for the part 1A.
Yeah.
And total is going to be 12 volts, and then you have to calculate the cost of
Right. It should come out that your total voltage is the same as your power supply voltage, which should be 12 volts. Yeah. So you're going to use a meter to measure the voltage. Now remember, is voltage a destructive or non-destructive measurement? Non-destructive. Voltage is the easy one, right? You measure voltage just by touching the resistor, or the meter, to the two sides of wherever you want to measure. So if you want to measure across R1, you just touch the meter to both sides of R1, and so on. So voltage is the easy measurement. Current is more difficult, right? Current is a destructive measurement. You have to partially deconstruct the circuit to do it. So for current measurements, what I like to do is I like to grab onto one side of, or to a jumper wire with one side of my meter, and leave the other side of the meter just with the alligator clip. And then you have to break the circuit apart to insert the meter in series in order to make the measurement. So if I wanted to measure the current through this green wire, for instance, what I could do is I could pull this green wire out of the circuit. What this has done is this has created two ends of the circuit. We've broken it apart. It's like tearing a rope apart. You've got two ends of the rope left over. So one end of the circuit is the end of this green wire, and the other end of the circuit is this hole in the breadboard. So what I'm going to do is I'm going to attach the two leads from my meter to those two ends of the circuit. So I'm going to attach the one lead to the wire, and I'm going to take the jumper wire from my meter and plug that into the circuit. So now the meter is wired in series with your circuit. Okay, all the current that used to be flowing directly through your circuit now flows through the meter and back into your circuit, and it gets measured. Questions about that? All right. So that's how you can measure the voltage and the current for this circuit. The second part of the hands-on lab involves making a lamp circuit. Now, this lamp circuit shows 3 bulbs, but I want you to cross out that bottom bulb and just put a straight wire from the bottom of L2 back to the power supply. Right? That's because our lamp boards only have 3 bulbs in them, right? We don't have an extra one. So we're just not going to use that bottom one. We're just going to have a straight wire there. So you're going to hook up the circuit like it's shown there. So this circuit is a little bit more complicated than the one that we built last time, but if you just take it step by step, you should be able to get through it, all right? So I like to think of it just like a connect the dots problem. You just go from one thing to the next, you check out where each one is connected, and you should be All right, so let's start with the power supply. The positive side, the top of the power supply, is connected to one side of L1. So that's what I'm going to do. I'm going to take my red lead from the power supply and connect that to one side of L1. Okay? Now, the other side of L1 is connected to the top of L2. So I'm going to do that over on my board. The other side of L1 down here is connected to the top of L2. Okay. A lot of people get confused about this part. Normally I like to arrange my circuits so that they look kind of the way that it's shown in the book. It helps me keep things straight. But we can't physically move the components that are screwed into this board, so that makes things a little bit tricky. But if you just see the one side of the L1 is connected to the positive side of the power supply, the other side of L1 is connected to the top of L2. If you can get that far, then you should be doing all right. So we've done that now. Let's move on. The top of L2 is connected to the top of L3. So we're going to do that. L2 connects to L3. And then the bottom of L2 is connected to the bottom of L3. So you can use one of these alligator clips. Connect the bottom of L2 to the bottom of L3. And then finally, the bottom of L2 is also connected back to the power supply. So I'll take the other lead, the black lead from my power supply, and connect that to the bottom of L2. Okay. So once we've done that, we've gone around the whole circuit. Any questions about that? Okay, then you're going to take your meter and you're going to measure the voltage and the current for this circuit as well. So you'll measure the voltage. Like I said before, it's a non-destructive measurement. You just measure by touching the meter to both sides of each component. Then you'll measure the current. And this one is a destructive measurement, so you have to partially deconstruct the circuit to do that. But just like before, when you break the circuit apart, you're going to have you're going to have two loose ends of the circuit, and you'll connect each one of those ends to one of the leads from your meter, and then measure the current. You have a question?
My question was, if you were to measure the voltage, would you go in the big screws or like to try like a dipole? Go ahead, that dipole.
You could do it either way. You would get the same reading. I would personally use the big screws because they're easier to clip onto, but you should get the same reading either way. Other questions? Okay, then that's all I wanted to say. Let me take roll, and you can have a break and get over to the lab.